Aaron?
Actually, yeah, I have a question. How are we evaluating, how are we estimating the maximum a posteriori probability for the parent trajectory? Like, what's the test or what's the procedure that we're using? I think I missed it.
That's a good question. Let me go ahead a little bit, and I can go over some of what we've already covered. So just, I'll come back to your question in just a moment. Let me just hit on some of the high points, and then I'll answer it specifically. So suppose our goal is to estimate the entire trajectory. This is different than what we've done with any other tracking algorithm and any other one that we're going to see for the rest of the term. So we're trying to find the most probable trajectory, not just the most probable state at a given time. And there's kind of the obvious ways to do it don't work or are really hard. One of the key insights is that we've got this recursive algorithm that we already developed where we can calculate the joint probability. So we can calculate this efficiently, we can calculate it recursively for any trajectory. So we've got an efficient way of calculating that, and we can evaluate it point-wise, even though we can't draw samples from it. That's why we can't just use it directly for Monte Carlo integration. Drawing samples from that is very... well, I didn't mean... So this ended up being the key part of the Viterbi algorithm is the idea that when you're trying to do the optimization, the key idea with the Viterbi algorithm is we can select the best parent. Every time we advance the state forward in time, we can look back at all the previous trajectories from the previous time step that span from 0 to n-1 and pair up the possible state value at time n with its most probable parent. And when you go through and you do this, there may be multiple values of the state that have the same parent, and there may be some parents that are abandoned. But we've got an efficient way to look back and find the most probable parent for every value of the state that we want to evaluate. And I know I haven't gotten to your question yet, but the short answer is that the only thing that you need to carry forward in time is the posterior for every trajectory you're considering. So if you've got some number of trajectories or some number of particles, call it, that represent the entire trajectory, the only thing you need to carry forward is what their posterior probabilities are. And here we've got the algorithm where we can identify basically how to calculate it. The only difference is that we don't need the likelihood term until we've found the most probable parent. Once we've got the most probable parent, then we can multiply these three together, and then we've got it. So that's the only thing that you kind of hold on to in memory moving forward. And I tried to emphasize last time that there's a big distinction between the joint map estimate or mode and the mode of the marginal. These are not necessarily the same. What the Viterbi is trying to give us is the thing that maxes over all the possible state trajectories, which state trajectory maximizes the joint posterior. And that is not the same. That's different in concept, and it's a different thing than asking the question, what is the most probable state at time n given all the measurements? These are conditional on the same things, but this is the big multidimensional joint posterior, and this is just the marginal posterior. So they're different. Colin?
I feel like a few weeks ago the joint posterior was x comma y, not a conditional probability.
No, that's not quite right. If you look back in deriving this, the way that we derived it, I think, is we started off with this joint of 0 to n, comma, and then I think I factored out just the measurement at time n, given all the past measurements. I'm doing this from memory, so this may be a little bit wrong. But I think this is the joint that we started off with. So there were these two things, and then we applied Bayes' rule to this in two different ways. So we set this equal to, and then we chose one thing. I think the first time I kind of pulled out y of n, and then the second time I pulled out something else. But ultimately what we were trying to get to, and what we ended up solving for, was this joint posterior. So this thing was just an intermediate step.
Okay.
Any other questions so far?
Can you quickly explain the notation there? So you have so the maximum value of all of your trajectories?
Yeah, thanks, and I'm
from
sorry.
Times 0 to n?
So I didn't clarify that before. So this notation means that you're trying to figure out, when you maximize this, over all the possible trajectories in this case.
Okay.
So out of all the possible values that the state could take on at time 0, time 1, all the way through time n, there's a huge multi-dimensional search to try to find the maximum of the posterior probability. But we're not merely maximizing over this variable. We're trying to find the argument that achieves that maximum. It's not, we don't really care what the maximum is. What we care is what trajectory maximizes that probability. And so this argmax notation simply means the argument that maximizes this function, and then the subscript indicates what you're maximizing over. So we're not maximizing, for example, over the measurements, because those measurements are things that we actually measure.
Yeah. Okay.
Yeah, thanks for asking about that. Any other questions so far? Aaron?
Yeah, okay, I'm having a little a hard time connecting the high level concept to the actual implementation. The P of x0 to n is the probability, so the joint posterior that's essentially a bunch of posteriors that are like state transition predictions, probability functions, and how do we get from there to picking, how do we translate that into picking which of the trajectories is the most probable?
Maybe if I sketch out a diagram, it may help. Let me try that. Okay, so let this conceptually be values that the state might take on as a function of time. Of course, in practice, this is going to be in whatever the dimension is of the state vector, but I'll just sketch it out as though it's a scalar example for the sake of illustrating. Let this be time. And if we start off at time 0, let's say we lay out a scatter of possible values that the state can take on. And it could be kind of a uniform grid like I'm sketching. It doesn't have to be uniform. It can be anything that you come up with. So you lay that out, you try to populate the space as best you can, and for every one of these starting particle values, you calculate what the posterior probability is using that recursion. When you start off, it would just be, there wouldn't be any likelihood, there would only be the likelihood, and maybe you've got an initial prior probability for the state. As soon as you go to time 1, then you also can lay out a scatter of particles however you like. And you could technically change the number of particles as well. It doesn't have to be constant, but you've got some number of particles at time 1. And now the problem that you need to figure out is for each one of these particles, you need to figure out which parent to connect them to, which parent that they're essentially going to adopt, and maybe would be a good analogy. So you look at this particle, and this particle you go back and you look at, if I connect it with this parent, then what's its posterior going to be? Same thing with this is a potential parent, this is a potential parent, etc. For all of the possible parents, you evaluate it for all of them, and one of those is going to be the winner. Let's say it's this one. So this one may be the one that maximizes the posterior probability for this particular particle.
Mm-hmm.
And as soon as you've done that, now these two are going to stay together from that point forward. You'll never have to go back and reconsider whether this particular particle, whether this particle here, should have had a different parent. And then, you go through, and the next time step, you do exactly the same thing. You kind of lay out a scatter of particles. You might advance them using your process model. You might try to lay out a uniform grid. There's lots of different ways of doing that. But then you go through and you do the same exercise for every one of these particles, where it goes back and evaluates all the possible parents to figure out which of all these parents might or does maximize the posterior probability for that particle. And as soon as you find a winner, maybe it's this one this time, and maybe this one had the best parent that was right there. Well, now you've got those three elements of the trajectory. So you kind of keep building up every time step.
So what you have, that makes sense, but you have to pick the most probable trajectory out of all the trajectories. So how do you sum over the parents, or how do you combine over the parents to pick the most probable trajectory, given that each of the assignments between parent and child is going to have its own probability associated with it?
I'm going to have to do this from memory, but the thing that we're interested in, the joint posterior from 0 to time n, given all the measurements from 0 to time n, ends up being equal to the likelihood times the prior times the previous posterior. And I should say this is proportional to. I'm not going to divide by the term that is the same for all of them, and that makes it have a uniform area. So when you're asking how do you go about this search, which is kind of at the heart of the Viterbi algorithm, how do you go about the search? So you're evaluating this particle and you're trying to find the parents. Well, basically, when you look at the parents, that means the trajectory from 0 to time n-1. So this is already calculated. This is something that you retain at every time step for the particle. So at time 1, you already have this value for all the potential parents. You have to calculate this, and when you multiply those two together, that gives you something that is enough to evaluate all the potential parents and figure out which one is going to lead to the maximum posterior for that particular particle. Does that answer your question?
Yeah.
Okay.
So in terms of data structure, we'll have, for each particle, we'll have one number for the weight, but also the history of basically the trajectory for each particle, right?
That's
Not
right.
just the
For
classification,
each
yeah.
particle, you've got its history of values.
Yeah.
So you've got the entire trajectory. And you also have, I'm going to refrain from calling it a weight because it's a little bit different. In this case, what you're really computing is the posterior itself,
Right.
or at least something that's proportional to the posterior, which is enough.
So it's like a pointer to the previous point in time, and then you can just traverse it backwards to get the optimal path.
Yeah, it could be.
For the trajectory.
It could be. And as long as I've got this kind of cartoon sketch, one of the things I want to emphasize is that a particle, more than one particle may have the same parent trajectory. And there are some particles that may end up not being selected as a parent, in which case you can forget about them for that time forward. So there could be some efficiency if each one is just pointing to its immediate previous parent, where some parents really get forgotten. There's no reason to keep in memory what these previous trajectories were, if they're not chosen at the next time step.
Two parents will never have the same child.
Does that mean you can just continually?
Let me think about his question. I don't.
Right, because you could have one, on a new time step, you could have two of them select the same parent as being the most probable. But you can't have one select two parents as being the most probable.
Every child has a single parent. That's
Correct.
where the biological breakdown
Right.
kind of fails.
Yeah, right. Right, so
So that does.
This
bring
is in a
up-
universe where there is no
instead of
marriage.
the other way around, where two parents can't share the same child.
I guess that wouldn't matter. It would still be parents even if they weren't married. Yeah, it doesn't matter. Yes, the short answer is there's only one parent for every child, but a parent can have more than one child.
What if you're dealing with like a discrete case, and then it's possible for the probability of two different particles from before to have the same probability as the maximum likelihood. You just pick one then, you say either of these trajectories is maximum.
Going into the modes, so they both be correct choices.
Oh, that's true, yeah.
And for what we're talking about in this course, you just don't have to worry about that. I mean, I know it's theoretically possible, but the probability of that happening when you're dealing with floating point precision and real stuff is just, it's too small to worry about. I mean, where that's going to cause you trouble probably is when you say, tell me which one is the largest, and then your code returns 2, and then things somehow fail because you think you're dealing with a scalar and you actually get a vector that has 2 elements. I mean, but that's really almost more of a coding issue than a math issue or an algorithm issue.
It shouldn't matter, right, because it's a Markov process, so the previous state value shouldn't affect it more than one time step in the past. So you shouldn't have to go back and say, if there were 2 possible parents, then, 5 time steps ago, then we might have to reevaluate which trajectory was most likely, because from time step to time step they were...
That's right. That would not be an issue. The only issue would be if you've got a particle, maybe this particle, and it's evaluating these 2 parents, and it turns out that when you calculate the product of the prior and the previous joint, that those products end up being the same. And so, how do you select from those 2 that are equally probable? Like, I'm going to leave that to you. But no one's going to complain no matter what decision you make, even if it's random in that case. That's not really the problem with the Viterbi algorithm. It does have a weakness, but that's not it.
Is it the fact that you have to square the number of particles and do that many computations? Because you have to assign a parent, you have to look at every previous particle?
That's one of 2 problems.
Oh.
One of 2 key problems, yeah, that's right. Yeah, very good, Walt. Any other questions on this cartoon?
Do we have to create new particles for the ones that weren't assigned any children and therefore aren't propagated forward?
No, every child will have a parent, because every child is going to look over all the previous parents and figure out which one is best. You'll never have an orphan. Yeah.
So where we split, you're gonna end up with an orphan. Or with a...
The parents can be abandoned. The parents may not have it. The parents, I'm going to get myself in trouble. The parents may be barren. Is that PC? Is that okay? Can I use that term? But every child will have a single parent.
I think it's a little bit confusing because you didn't draw the optimal for that time step 2 for all of them. So those 3 points at the top look like they don't have any parents, but they actually do have parents. Well, going back the other way, yeah.
I get you.
How's that?
The top one still means it.
Oh, yeah, you're right. But only going back one point in time. How's that? All right, thank you. Made it. Now it's complete. All right. Colin?
Depending on your process model, could you speed up the computation by just calling the parent the one that's like closest? in terms
Well,
of
you
distance?
can, but then you're not doing the Viterbi algorithm. You're doing something else.
Can you use
No,
it to
it-
start your search?
We'll talk more about this in a bit. You guys are hitting upon one of the key weaknesses of the Viterbi algorithm, which is, oh man, for each particle I got to search over all the parents, and if you've got like a random walk model, this one's way down here, there's no way this is going to be the parent of that one. So why would you even check it? Why spend the cycles even computing it? So then maybe when you're looking at the parent of this particle, you only want to look at those that are reasonably close, that have a reasonably large transition probability. So now we're getting into ways of doing optimizations where you can reduce computation with a relatively small penalty in terms of accuracy. And there are ways of doing that, but it's way easier to think about that in this one-dimensional case than it is in a multi-dimensional case. Remember, in general, this is going to be a high-dimensional space, not just on a vertical axis. If you've got a 10-dimensional state vector, then how do you know which parents are going to be candidates and which ones aren't? It becomes harder, and that there are things you can do, but it's harder to do that optimization in a high-dimensional space. Let me move on. I'll take more questions in a bit. So this is hitting on some of the points that you guys already picked up on. It's been a while, but a week ago we talked about the auxiliary particle filter, and the auxiliary particle filter also had this notion of best parents. There was a pre-sampling instead of a resampling with the auxiliary particle filter. And so there was this idea of best parent particles, and we're seeing kind of a related idea with the Viterbi algorithm. So I wanted to compare and contrast. The Viterbi algorithm is searching for the best parent, but it's computationally expensive, as well, and the rest of you are picking up on, because for every particle you got to search over all the parents, and that requires order NP squared operations, where NP is the number of particles or number of trajectories. The auxiliary particle filter does a random sampling, and so it's more efficient. There's still that sort operation. That sort operation to do the pre-sampling requires NP log NP operations, which is more or less linear. This log NP increases so much more slowly than the NP factor that I tend to think of this as being very similar to having linear scaling with computation, even though that's not technically true. But it's much cheaper, especially for a large number of particles, than the Viterbi algorithm. But it's giving you something very different. That's giving us posterior represented by impulses. It's not giving us a way of estimating the most probable trajectory. So we get something different from the algorithm than we get from the Viterbi algorithm. So other than the fact that they're both picking on parents, really this framework is completely different than what we looked at with the auxiliary particle filters. All right, so you've seen this before, so I don't need to go through and explain this. I don't know from a teaching standpoint whether it would be better to introduce a new state space model every time and say, here's another thing you could think about, and take the time to go through and explain it and defend it the way I'm making you do that for your homework presentations and your projects, or if it's better to just say you've seen this before, so you're already familiar with it, and we can just move on. You know what the posterior is going to look like, and it's really the algorithm that I want to spend time on. Is that okay, or does that bug you that you keep seeing this car, this poor, pathetic car that Amit improved upon?
You said you were going to lecture on system identification, and if you keep using the race car with the system identification slides, then that'd be really annoying.
Yeah, I agreed. I don't remember saying I was going to give a lecture specifically on system identification, but I will talk about modeling. I think you went from modeling to system identification, and it's recorded, so I guess we can go back and look, but system identification could be a whole course in itself. In any case, today we've got the car going around the track in its random way. You've seen it before. We've got design decisions just like we had before, except this one has an error in it. And I apologize. I tried to clean these up so that I didn't have these errors. This is wrong. We don't have to pick an importance density, and I did not choose this as the importance density. I chose something else. I did choose 100 particles, and this was really kind of to push the limits. And this is, I didn't estimate the mean, obviously, either, so that's also wrong. I apologize for that. You have to go back and clean up that slide. So what I did do is probably going to surprise you. I have to.
Why do you need an importance density?
Pardon?
Why do not you need an importance density?
I'll explain. Give me 1 minute and I'll answer that question. So you've seen this before. This is just a sketch of the measurements and what the trajectory of the car is. Again, 100 particles is what I'm using. And there's nothing else here that is wrong. Okay, here's what I did. Kind of like Amit assumed that he knew what the average velocity was of the car, as well as the limits. There were some assumptions there. I assumed in this case I knew what the average velocity of the car was. And at every time step, I laid out a uniform grid of possible states that it could take on. I didn't use the process model in this case. There's no reason to, really. Instead, I laid out a grid of possibilities of where the state could be at every time step, and I just increased basically where the center of that grid was over time at the same rate as the car. And the nice thing about this is I don't have the problem of sample impoverishment. I've got the whole thing covered really densely, which is really nice and turned out to be to produce some really interesting results. Does that bug some of you? I did that?
In the multi-dimensional case, it would bug me.
Very good. Yeah, and that's the second problem with the Viterbi algorithm. And I'll say more about that shortly. But yeah, in the multi-dimensional space, then you're kind of stuck. I don't know if we're going to hear about a GoalRiz with your project, but I was working with GoalRiz on a project for months where we were trying to use a Viterbi algorithm. And one of the big things we ran into is when you're trying to represent an orientation, there's 3 degrees of freedom. We were trying to estimate our orientation continuously. And 3 degrees of freedom with 1 degree of resolution ends up being like 1,000,000 possibilities. And if you've got 1,000,000 possibilities, and then you go to the next step, and you've got 1,000,000 squared computations, you don't have a solution. You've got a problem. So that was one of the things that we stumbled into. That was like, shoot, this isn't going to work quite as easily as we were hoping. And then you have to get into those kind of heuristic optimizations that I was mentioning before. So the green line is showing something weird, and I hesitated to even include it, but I did anyway. At every given time step, we've got the entire past trajectory estimated. But often what we're interested in our applications is what's your best guess of what the state is. And if you're going to do that with a Viterbi algorithm, the only thing it gives you is the best entire past trajectory. But you could pick off the last element of the past trajectory and say, my best guess of what the state is at this time is the last element of that entire trajectory. And you go forward 1 time step, you've got possibly a different trajectory, and you do the same thing. And so what we're looking at here is the last estimate of the most probable trajectory over time. And that can change rapidly. We're not looking at the best trajectory itself. I can plot that, and I will in a minute. At this time step, if we've seen 100 measurements, I could plot the most probable trajectory where we're looking back over time to see what that entire trajectory was. But what I'm plotting right now is if you were using this in a real-time application, where you really just wanted the best estimate of the state at that time, and for some reason you were choosing to use a Viterbi algorithm, probably what you would choose is the last element of the most probable trajectory. And so I've plotted that over time for this example. And you can't see much here other than to see that clearly this is going to be within the range of where I laid out the possible trajectories as being. That's the only thing you can see. One other thing that may help you in understanding this is I've got 100 points laid out on this grid. I mean, they're so close together that with the dots or line thickness I used, it just looks like a block of gray. But there's actually 100 distinct trajectories there. And at this point, these trajectories go all the way back. So at time 100, there are trajectories that I'm continuing to evaluate that even though I say this is a very improbable place to be, at that particular point, I've got an estimate of what the most probable trajectory is that would end up right there. And I've got that for all 100 points. So you don't have that sample diversity problem in the sense that the particles have not left this region. If suddenly that becomes probable somehow, you can recover it with this, where you can't with other particle filtering techniques. You can guess the state is going to be any possible place, and it will continue to consider that all the way forward. So that it's nice that it has that property.
So that is why you would do the grid type approach instead of using what you know is from the starting state and a process model, something about how the system advances to set up a different grid, or maybe it just doesn't.
You could use a process model. There's nothing wrong with using a process model. If you did that though, you would end up with some holes, because things are going randomly, and you'd end up with some overlap, because when you're advancing the state forward from one time to the next, if you're doing this randomly according to your process model, it's quite possible, just due to chance, that some of those particles are going to be very close together, and some of them are going to be far away from where you might want to evaluate. You don't have any kind of constraint with where you choose the particles to be. We did with the others in some sense, that they have to be done randomly from some kind of importance density, and you need to know what that importance density is. That's completely gone from this framework. You don't have to do that. You could lay out a grid, or you could use the process model. You can do anything you want, but it doesn't have to be random anymore. There's no requirement in this algorithm that when you're picking the candidate states you're going to evaluate, that it's random. And there's some advantages to having it not be random. In the one-dimensional sample, it's easy to say, well, great, I don't have any loss of where things, where the space is covered. I've got the entire space covered. That becomes hard in high dimensions, but at least you can do it.
And then that your choice of 100, it was like a range of 400. So that means that you only have a resolution of 4 degrees or meters or whatever that was.
That's a good point.
That you could possibly measure to. That's like your maximum accuracy then, or your estimate would be 4 meters.
Yeah, that's fair. Yeah, good point. I hadn't even really considered that.
Not criticizing, or just to understand.
No, you're right. It's accurate, and I hadn't thought that through. I probably should have, although it's not really one of the main points I want to make. But with good design, you would absolutely want to consider that. You're right. Yeah, that's a good point. Okay, there's a lot on the slide, and as usual, I have a lot to say about it. Whenever we look at one of these posteriors, I get excited because there's so many cool things happening.
Can you turn the lights off?
Yeah, boy, there's... When I was... so this is the optimal importance density as before, and I can see when I was doing the calculating the optimal importance density, I should have chosen a finer resolution, because you can see some of the binning effect. Those don't look as smooth as they could be. I don't know why I did that. It doesn't matter. So as usual, what's happening here is we've got the position of the car on the track, and I think the units are radians. We've got time here. And according to the posterior, we had a mode that kind of went down, and there was a small probability that the car went up. The measurements were more consistent with it going backwards. It turns out the car was actually going up, but the measurements gave stronger evidence it was going backwards. And then suddenly the measurements were clear that no, the car is actually up here. And we hit another bifurcation here. This is probably when it went around the track and hit the other edge. And so again, there was a small probability that went up, and mostly the measurements were consistent with it staying down. And then it looks like we're on the edge, and there's kind of two modes that are kind of blurred together there. And then the main mode is up here, and then there's another one that's down here that was less probable. One of the things I'm showing the true state in red, so that's where the car actually was. We don't care about that so much. The marginal posterior is what's shown as the colored image, in the grayscale. The true, so-called true mode, the true mode of the marginal posterior. So in this case, I'm just using the optimal importance density, and I'm figuring out of all this, for each vertical slice, where did the maximum occur? And that maximum is shown in blue. And this true mode is different than the last element of the most probable trajectory. We've got the mode of the joint, and then we've got the mode of the marginal. And this is just showing the true mode of the marginal. That is not what the Viterbi algorithm is trying to calculate. And I included it on this slide mostly to drive home and try to make it clear that this is different than what the Viterbi algorithm provides you with. The mode of the marginal is different than the mode of the joint. And the last element of the mode of the joint is also different than the so-called true mode, or the mode of the posterior. So the only reason that's there is just to make it clear that that's different than what the Viterbi algorithm gives you. The thing I've labeled Viterbi in green is the same as what I had on the previous slide. This is the last element of the most probable trajectory at every time step. So as you're going along, and I've got 100 points, I'm always evaluating 100 possible trajectories. And we're going forward, and you can see there's a huge jump right here that is a very improbable jump. And that's okay. What happened is we got a measurement where suddenly the most probable trajectory was the one up here that I was tracking all along, and the trajectory that was, you know, associated with this point is suddenly not the most probable trajectory, so I'm no longer displaying that. I'm always looking at the last element of the most probable, and there was a switch from what was the most probable from being down here to being up here at that time step. That's fine, there's nothing wrong with that. You can see some more switching over here where these are clearly not part of the same trajectory, and the reason you know that is that based on our prior, it would be very improbable to have a jump of that magnitude. And so that has to be switching of trajectories, of just what is the most probable trajectory at that particular time. The other thing that I'm plotting is the Viterbi trajectory at time 100. So in yellow is at time 100, what's the most probable trajectory? And now unwind that and look back in time at what that entire trajectory is. So this is really the thing that the Viterbi algorithm gives you, and that's where it is. This was disturbing to me when I looked at it. It didn't bother me at all that the last element, that the green didn't match the blue, because I didn't expect those to match the same. They're different things, fundamentally. And so this looked pretty good. One of the things I thought was really cool and kind of beautiful is that the estimate here of this transition for the entire trajectory is I use the word beautiful too much, but it's really nice. It's smooth. It's right exactly, more or less, where the car actually was. And it was able to pick that up because by the time you get up here, it's clear that the car wasn't down here. It wasn't part of this mode. And this is always evaluating up here, what's the most probable trajectory looking back. The only way you could get up here that's consistent with our process model is by a series of steps that are smooth. And so although at the time there's nothing in this region that would tell you that, you know, given the measurements you've seen to date, it's pretty improbable that you would be there. By the time you get here, looking back, that's more or less exactly where the car had to go. That was the only path it could have taken. So for the first time, we're really seeing an element of smoothing here, where when you take into account these future measurements, there's a very smooth transition over this region, which is really nice. We haven't seen anything else that can do that so far. But the thing that bugged me when I looked at this is, what on earth happened here? How can that be? This seems to be a very improbable place that the car would be based on the marginal posterior, the thing that we're visualizing. You know, the measurements are more consistent with the car being up here. So how did we end up with this being the most probable trajectory? Why didn't it somehow figure out that the car is up here like the marginal did? And you know, I looked at let's have a bug, go back, look at your code, think about it, do some more experiments, and I finally figured out that no, this actually is right. At this time, this is the most probable trajectory. There is a trajectory up here, you know, there's a particle up here, and it looks back over time, but that's actually less probable, given all the measurements to date, than this trajectory that we're seeing. And this also shows very clearly that the last element of the most probable trajectory is quite different than the mode of the marginal. There's a big gap between the two there.
What question on that? Isn't the green line your marginal from your Viterbi? Like the most, what's the green line again? I thought it was the furthest step of the current most likely Viterbi trajectory.
Are you trying to embarrass me today, Walt? No, that's an excellent question.
Why they don't match.
Yeah.
I thought the green was the last stop of the yellow.
The difference is, it's the difference between the joint marginal, or the joint probability and the marginal probability, right?
No.
Those don't have to be the same. The green one is just the highest marginal probability at that time point.
No, that's not right. What Walt asked is the right question, and it points to a bug, a problem. I think what happened is that the limit of the display got clipped off the last one. I can't quite make it out, but I think what happened, you can see that there's kind of switching back and forth between these two, and I think there was a switch that happened right there. So actually there's one more point that I'm not displaying, I think, where that is the most probable trajectory, and this green would have flipped down to it if I had displayed it correctly. So I think this I think that's the problem, is I just didn't, I cut off the display 1 point earlier than I should have. But yeah, that's something else I need to go back and fix. You're absolutely right, Walt, this should have been the same. It was a really good point. And hopefully, Ethan, that helps a little bit with your understanding as well, because
Yeah, that's right, it's the last point of the most probable trajectory.
Yeah.
Point, so it should match.
right, they should match.
And back on the like around 25 there, you had all of this like high, strongly grouped mode in your marginal that's bringing you down there, and it's been basically unimodal for a really long time, and you do have some kind of tails that are tailing off up there, and then all of a sudden you get one measurement. You basically have the two modes there at time step 25, where you start to have something else there, and it immediately jumps to that other one. It seems like from an intuitive point, you had like all of this, weight saying, hey, we're going down there, and even I think that one where it switches, it's already switched before you start to lose your probability on the next step there. I'm just amazed that it jumps over to that other section so quickly.
From
It
the
seems like that one trajectory would have been weighted so much more, that we had all these consistent measurements.
It's a bit difficult to estimate the exact relative amplitudes of those two different colors, right? I mean, are they, is that 1/2 of or a double?
You can't really see how high these peaks are. The color scale, saturates at dark black at some point. So you're right. I should have raised the upper limit where it hits black, because you can't really visually make out how high those are. But yeah, it's pretty cool. And it's also true that we're only looking at the marginal, so we can't really see what the Viterbi algorithm is seeing. I'm not plotting. I guess that would have been interesting maybe to plot what the probabilities were of the joint as well. That would be a great slide to add, actually. That'd be really neat to see. I hadn't even thought about visualizing it that way, but I totally could do that. So we could see, why is this peaking in peaks? And we would see something that would look a little bit different than this. That way we would then see, why is it way down here rather than up there? Because the joint is clearly giving us something very different than what the marginal is giving us. That'd be really nice. I'll add that if I can remember it.
Is it true that Viterbi, like the probability of each of those points, is that going to approach the same PDF? Like we can guarantee with the Monte Carlo, it's going to approach the PDF?
Andy, I didn't understand your question.
So when I look at this Viterbi, right, you're basically saying I have a bunch of particles that are uniformly spaced, right? And they all have a weight associated with them, which was probability that the state would take that value, right? Which to me looks like a lot of weighted Diracs, right? Which looks a lot like the probability density function at that point. So we should be proved earlier that in the Monte Carlo case that'll approach with the particle filter, that'll approach the actual marginal. Did we prove that Viterbi filter, that if I add more and more and more of these points in my grid, that'll approach the true PDF?
And you're asking, does something similar happen here?
Well, is it true that we can prove that that'll be equal?
Yeah, I'd have to think about that. In this framework, we don't have Diracs, and I don't know if you can really introduce them and say what we have is kind of equivalent. I'd have to think more carefully about that. The way this framework is usually explained and presented is that we're always trying to get at the joint posterior, and it turns out we can actually compute what the value is of that joint posterior at any time step. So why not just use that? If you can figure out where to place your particles, then this algorithm is kind of an efficient way of considering how to link from one time step to the next, where you never have to go all the way back in time and consider brand new trajectories. Using the fact that it's a Markov process, whatever the parent is of this particle, it doesn't matter what its children are. That'll never affect what the best parent is for that particular particle. So that's where the efficiency is gained with the Viterbi framework. But you're really just evaluating the posterior probability. And so there's there's no need to think about the directs. We're not really trying to estimate a density. We're just calculating the posterior, and because we're trying to find the mode, we really just need to figure out which one's the biggest, which is easy. So it's different. And if I did that visualization, it would be more that of a group of possible locations where I happen to evaluate the probability. Just what does that look like? And I could do that over any grid I wanted to. In fact, I could do it over exactly the same grid here. You know, rather than having it grow over time, I could have just said, give me uniform spacing from 0 to 12 or whatever this goes to. Could have done that. Maybe I should have done that because then it'd be easier to create the image.
You could also just use your importance draw, right? But then
Yeah.
you just assign the weight from Viterbi rather than using the SIS weight update.
That's right. You don't need the weights, but you can certainly use your process model to move particles forward in time if you want to. Yeah.
Auxiliary Viterbi.
Yeah, or you could use auxiliary Viterbi, exactly.
Is that a thing?
It is now. Congrats.
I don't know. You know, I mean, so maybe one of the things I probably haven't made clear in presenting this is that this is kind of out on the edge. I've seen very few cases where in the continuous state case, you know, we're always thinking about the state vectors being some set of real numbers, not just taking on discrete values. So we're not like in a communications framework where we've only got a certain number of symbols and it's a finite number of symbols. Instead, we're thinking of the state as taking on real values. And I've seen very few papers, very little consideration of using the Viterbi algorithm with a continuous state vector. And there's good reasons not to do that, but there's also really good reasons to do that. And it seems like people have just kind of overlooked that. So what I'm presenting to you here is kind of on the edge. Most people don't do this. I think there's good reasons to think about it, but that also means that there isn't really a set of best practices for doing this, doing what I'm describing, which is an opportunity for research. I mean, if some of you were interested in doing research on this, research project or thesis or something like that, I'd certainly be interested. It seems like this has potential. You know, when you look at the trajectory here, I mean, that's just, it's beautiful. It looks like it's doing the wrong thing out here, but it's actually doing the right thing.
Maybe if we give the 100 more samples, it will snap back.
Oh, funny you would say that. So I consider that, and there's a hint that would occur because you see the most probable already switching between these two. So I extended duration exactly as you described.
Worse.
And yeah, it gets worse. But you know, it's curious because this really is the most probable trajectory at that time. It really is more probable that the car went backwards for an extended period of time, even though it's got an upward bias. But man, you would just lose it with any of your particle filters. You wouldn't have any particles down here. You wouldn't see that portion of the space. With the resampling or the pre-sampling, all your particles would be up here on that mode. There's no way that you would have captured this, but it's the right thing. The Viterbi algorithm is doing the right thing. And the reason I know that is when I saw this, I was like, gosh darn it, I've looked at my code, I've looked at the theory, I know it's mathematically right. Let me go a little further forward in time and see if it comes back. And sure enough, it did. And when it did so in really a beautiful way. If you look at the entire trajectory going back, it's really good. It matches where the state is really well. It manages this transition beautifully. I mean, it's doing smoothing, but boy, you couldn't have drawn a more beautiful kind of fit of where things are, and it matches where the car was, as good as you could expect any estimator to for this particular problem. So, yeah, and it really was doing the right thing. It wasn't the most probable trajectory for a very long time. Really was down here, and then finally, it turned out this was more probable at that point in time, and you use that going forward.
So,
quite surprising.
So would it be possible to run a particle filter and calculate a bunch of marginals and then keep those particle values and then apply the Viterbi to those pre-calculated particles to get the best possible trajectory from all of those particles that we calculated?
Yes, the Viterbi is pretty compatible with almost any of the particle filtering algorithms. But there's a few downsides to kind of doing a mashup or blend of the two. One disadvantage is you're going to be burning all your computation on the Viterbi algorithm unless you get clever about that optimization of which parents you're looking at.
I'm just wondering if you could do it offline, like during, like in my physical system, if I'm doing some kind of control algorithm, have it use the particle filter, and then if I want to look at it later to see what was the optimal trajectory, I can compare it to what the
Yeah, sure. Yeah, you can certainly do that. You can certainly do that. The other hazard of doing a mashup, even if you're doing it offline, is that because of the resampling or the pre-sampling or whatever you're using, again, you're not going to have visibility down here. So you would be blind to things. You would kind of fall into that one of the limitations of the particle filters, that so-called sample diversity problem. If there's a very improbable mode, and it may become very probable later. You know, we've got kind of an example here. You could run into sample diversity with a particle filter. We didn't. But in an extreme case, you could imagine that the particle filter with the resampling doesn't have any particles up here. And if it doesn't, you'd have a heck of a time getting it to recover and rediscover that mode when all the particles are down here following this one. So you got to be careful, or just use a heck of a lot of particles, which is what most people end up doing, because Moore's law has been generous and computation is cheap. Yeah, but isn't it cool to see?
So, so 2 points. One is that so this is somewhat like Viterbi coding in communication, where having the Viterbi coding it improves noise resilience, right? It's more robust to noise. But if the noise becomes worse enough that the code breaks, it breaks more catastrophically, right? For a large chunk of data is gone because we choose a different trajectory. I mean, it's the same thing.
I didn't quite follow that last bit. A large chunk is gone. What do you mean a large chunk is gone?
Okay, so here we maintain the trajectory from time zero, but in a lot of practical communication systems, there is a code length that we use. A finite code length. There's a way to propagate that, kind of moving window kind of way. And if noise was big enough to cause the coding to fail, the entire chunk, which is as big as the length of your coding, is basically wrong. So instead of random error here and there, you have like whole chunks lost, and whole chunks right.
I see.
So so that's similar. And also another thing is that if we could always so this gives us a way of kind of smoothing, like looking.
Yeah.
Even if it was wrong, it was wrong always right towards the most recent samples. The past was always accurate. Right? So it's like smoothing there.
That is a good point. Pretty much all the trajectories out here figured out that transition had to occur.
Yeah.
So if you look back and you're looking at how many parents eventually get sort of orphaned off.
Wait, hold on. Look at that segment between 165 and like 175. That's flat, or it's a line. It's running up against the bottom of your your grid.
Yeah.
Oh,
So it's
yeah.
possible that the only reason why it snapped back is because your grid forced it to.
That's very funny. You're right. Good observation. I had never seen that before, but yeah, you're right. It's hitting the bottom of the grid there. Good point.
Yeah, I don't like this.
Yeah, I'm confused why the most likely trajectory wouldn't match closer to the marginal end. I get that they're not the same probability. It's just that.
You know what I should do, and I'll try to do this for next time, is lay out, just like I'm doing the computation where I'm doing the numerical integration of the marginal posterior, I could choose exactly those same points as the grid and evaluate this on that so we can see the visualization of what at least, well, what would that be? That would be the joint for all the trajectories at the points where they're at that time. I mean, it would create a different kind of image that would give us more insight as to what's going on. And it would also resolve whether hitting the bottom of my grid here is what caused that to snap back or not.
It could just also be that the most likely trajectory was outside of your grid that you were integrating over.
Yeah.
For the Viterbi, which is why it never
Oh yeah,
actually
it may be that may exceed the upper limit. Oh my gosh, yeah, good point. Because I only I only sketched where the true was relative to the grid out to 100 on that previous slide, so I think I only went out this far. And maybe these are getting up there.
But in the first picture, the true was always in the middle
Within.
of that.
But that only went to time 100, I think.
Yeah.
This is
Although-
a random, sorry.
That's the slope. It seems like at that slope, this stuff would still be within range.
So if, when you calculated that area, you did the Viterbi area over, right? That you're integrating over, that area there is based on taking your prior and moving it forward like a certain number of sigmas out, right? Or how did you pick that range there? Because it would seem that,
It's just the
given that
average
you
velocity of
given
the
that you
plane.
didn't have any information about the measurements, the only way they could pick a range for the process to go through would be based on your initial prior, you know,
Right.
whether the variance would explode and the possible places that it could go would be really big.
I know you're asking about the prior, but I didn't catch question.
So when you did the Viterbi, you picked an area to integrate over, right? And you said, I think that the process is only going to be in this area, right?
Yeah. Right. And that looked, roughly, I guess I should use blue.
Yeah,
I don't know if I can quite match the slope, but it was something like this.
right. You said that based on my velocity, this is going to go forward like that. But the width of that band there, right, is, how did you pick the width of that band, right? Like, it would
Oh.
seem, if you just pick that width based on the prior, like I know that its initial position can be in this and it keep going forward, that isn't accurate, because that's assuming, we all know that the variance would increase over time.
Yeah.
So it's not bounded. Yeah.
So you're absolutely right. It would have been better if I was doing a careful design to have this bounds probably grow. If that was the basis for doing that. And there's lots of different ways you could do it. I mean, you could also look at, you could use the information you have to figure out where you're going to lay out the points you're going to evaluate at the next point in time. So I could have a very wide band that's just kind of following where maybe my last estimate of the state is. You can put points wherever you want with a Viterbi. And my design choice was by no means optimal. It was really just designed to be able to illustrate what the algorithm is doing. And Aaron very, very nicely pointed that I failed here in my choice. And certainly if you were going to make an optimal choice, you would do this quite differently. There's better design decisions you can make for how to lay out the points in this particular problem. Yeah, those are all good points.
This wall, you can see at time 100, it snaps down to
Yeah.
where it was.
I do see that.
That was the point that wasn't graphed on the first slide.
I'm just-
Oh yeah, right at 100, so it is there. Okay, mystery resolved.
One of the
One mystery. Yeah.
Yeah. Just-
Yeah.
It seems like the maximal joint should end in the same state as the maximal marginal, just because if that's the most likely state, why would your most likely trajectory not? I guess because the ones immediately preceding it were so much more likely. So that's possible.
Yeah, it might not be. And I was surprised to see that it didn't in this particular example. I think Andy hit upon a very nice point earlier too. It's quite possible that my grid was too coarse and that I'm skipping over the peak. But even skipping over a peak, it seems that if the joint is anything like the marginal, then it's hard to imagine that the grid was so coarse that I was skipping over a big peak there, and that ended up being bigger.
I don't know if it's necessary that you skip through the peak, but was your band there that you're integrating over really from 0 to 6? Because it could have been all the way out. Like if the race car moved too quickly that it was out faster than you thought it could actually possibly go, then its real position would be
over the average.
over that top blue.
I'll have to check that. I'll dig into this more and come back to you with some more results. You guys are asking really good questions. And again, that was a really nice catch down there that I had overlooked.
Plus the gridding, I think the way you explained it, you're offsetting the entire grid by the amount. So it's not like, the entire grid by the average speed.
Yeah, it's just growing up linearly at
Right.
what the average speed was.
Which may not be an even multiple of your grid spacing. So at each time point, maybe you have your first ones are like 0, 4, 8, and the next time it's at 2, 6, 10. So that you have is like offsetted your grid, so there's states where it could be is kind of.
Yeah, that's okay though. I don't think there's anything wrong with that.
It can be fun.
That's fine. It's just it's harder to make an image out of that. Is all. But I think that's fine. I'll come back. I'll do that image that I described. I think that'll shed a lot of insight into what's going on here. And I'll use a finer grid to make sure that I'm not just skipping over a peak. It may be that the peak of the joint is just much narrower, and maybe I am skipping over it, and it is actually up there. That's possible.
Or you could use more than 100 particles.
I could, yeah. I probably will. All right. So let me move on, and I'll take some more questions. So, as I mentioned, and as we've already hit upon, there's two big weaknesses of the Viterbi algorithm. I mean, there's good reasons that people don't choose it for continuous state space tracking, even though I've suggested that it has, there's some good reasons to use it. The first one, I've kind of got these out of order, as I mentioned, is that it's much more computationally expensive in its basic form than the particle filters we've talked about. And as we've discussed, there are ways that you can consider mitigating that. There are algorithms for finding nearest neighbors quickly, and you might be able to adapt them and have a way of really only evaluating a subset of your parents, or using some bounds where you don't really have to do the full computation in order to eliminate one or more candidate parents. There are techniques that can be used for that when you're doing a Euclidean high-dimensional search for the nearest neighbors. So something like that might be possible that could enable you to make that more like linear in the number of particles, or get that closer. And you know, you guys were already thinking of some ideas. If you're advancing particles forward from your process model, you could have every parent sort of spit out a certain number, maybe 5 or so, and then just evaluate. I guess you could evaluate children rather than evaluate parents. You could advance a particle forward a whole bunch of times and then just pick the one that's most probable and leave the others out. Essentially make them sort of barren parents at that point. So there's a number of clever ideas where I think you could potentially overcome that in a lot of different cases. The other big weakness, and the one that's much more scary and harder to solve, is that it's very hard to densely fill the state space with good candidates. So, you know, one dimension, you're like, just lay out a grid. It's easy. It's great. You don't have to mess with random numbers and, you know, just go. I really like that. It's much more elegant. I finally got away from the random number generator for resampling and moving the particles forward. But then you run into the curse of dimensionality. You know, it's very hard to know where to place those. And if you try to do the equivalent of uniform grid, it scales exponentially with the dimension, which is just terrible. So it's just really hard to densely fill a high-dimensional space. But as many of you suggested during our discussion, we've got particle filter algorithms, we've got the process model, we've got a technique by which we can herd particles to good possible locations. But again, when you do that, then you may run into diversity problems where you don't have some of the space covered that you really do want covered. So, you know, the good news is you can place things wherever you want. You can evaluate probabilities anywhere you want in the state space. The bad news is that now you've got the responsibility of figuring out where that's going to be, and that responsibility turns out to be a heavy burden. So that's the flip side. But again, I think there's room for cleverness for overcoming both of these weaknesses, and that's why I think this is potentially a kind of a ripe area for research. It's a good algorithm fundamentally, I think. So here's the last slide on this topic and the pros and cons. So there's no more importance density. You can use it if you want to, but you don't need one. You don't need a random number generator to do this. You can really place particles however you like. It doesn't have to be random anymore. It had to be random with the other particle filter framework we're using. There's no weight updates. All we're keeping track of is the joint probability for each particle. We don't have to worry about the sum of impulses to represent some kind of posterior. And we kind of get smoothing for free, which might be valuable for some applications. For some applications, it might not be. It was this smoothing aspect that I was interested in the research project I was working on with GoalRes. And it turned out that it wasn't any better than the incentive Kalman filter, but that's really what we were after. The disadvantages, because we no longer have the posterior, some kind of representation of the posterior, we lost confidence intervals. You didn't see any kind of approximate confidence intervals. We're just finding the most probable trajectory, but I can't tell you how good it is. It can only be used to estimate the mode. You know, within this framework, you can't estimate the mean. We don't have any posterior probability by which we could try to calculate a mean or percentile or a median. It's just the mode. That's all we get out of this. Lots of computation, you know, much more than the particle filters. And it doesn't find the most probable state. It only finds the most probable trajectory. For some applications, it may be that what you really want is the mode of the marginal and not the mode of the joint. It's application dependent, but it may give you something different than what you actually want. And I think that's it. You guys have any other questions?
Yeah.
And Scott, would you turn the lights back on?
So that, you know, the green curve that you plotted, can we think of them as the marginal, given only the trajectory, the Viterbi trajectory posterior, right? Or given the trajectories, right? Joint probabilities. How do we know what's the most? Like we pick the mode, right? Why is that mode not the marginal?
Yeah. I was afraid someone was going to ask that question. I think I can sketch a cartoon that will answer it, though, I think. I should have thought more about that, because I thought someone might ask, and I think I can make up an answer. Let's see. See if I had enough sleep last night. Let me think. Oops. So if this is x of n minus 1, and this is x of n, let's see, I want to kind of sketch out something where the mode is different for the marginal. Maybe, you know, before I had this kind of horseshoe thing, and it's a little bit hard. Maybe I can make a kind of a pseudo color scale here. I need to use the app on the fly. And if I make this the darkest, and we sketch out what the marginal looks like in this case. Oh, you know what I can do? I know what I can do. I'm going to put a whole lot right here. Ah. Okay. So when we sketch out what the marginal looks like now for x of n, because I created this where it's improbable, but when you're integrating up all of the PDF for x of n minus 1, that ends up giving us a peak at that point. And then there's a smaller peak here. And so this marginal might look something like this, where the mode is right here of the marginal, but the mode of the joint is right here in a very different location. That would work. So this is an example where they're in different places. Are you persuaded?
Yes.
I think I just needed one example where the peak, when you're looking across this in 2 dimensions, and of course we're looking in many more dimensions, is what we're really trying to do, or what the Viterbi algorithm is doing, but a cartoon in this 2-dimensional space, I think, is sufficient. If you kind of think of this as a kind of a rough color map, where that's the peak of the joint, but when you integrate the total area accumulated across x of n minus 1 to get our marginal probability, the marginal probability might look something like this, because we're accumulating the area of all of this possibility over a wide range of x of n minus 1, when really the peak of the joint is in a different place. So conceptually, that should be enough to persuade you
Okay.
that it's possible, at least.
Yeah. And so we use the kernel smoothing to get posterior from the particles. We could do the same thing here. No.
You can't. You can't.
It's not the same thing. Yeah.
It's not the same thing, because the critical thing that we had with particle filters was the weights,
Right.
and that enabled us to capture something that was a representation of the marginal posterior. But now we're just kind of picking points wherever we want and evaluating what the joint is at those points only. But there's no way to then take that evaluation and say, okay, now we've got the marginal.
Okay.
I mean, you have to somehow do an integration.
One last question. So in Viterbi, how we choose the parent at each stage. So we compare with all the possible candidates and pick one, the maximum, right? Could we instead of picking the maximum, could we combine all of them and pick what will be more like the marginal at this point at a step n? Like if there are a lot of previous parents which lead to this the current point, then looks like there's some information there about picking up the more probable.
Okay. So using that kind of diagram I had before, where I was sketching out kind of conceptually where these might be. This was the state, and this is time. And you say, we've got a case now where there's a convergence on the same child, is that right?
Right.
So when we figure out where the best parent is, it turns out that all these parents ended up kind of
Right.
pointing to the same child.
Right. And say if you had a fifth point, which was the strongest in terms of trajectory.
I'm sorry, hold it. This is the wrong diagram. This
Right.
can't be.
Right.
I screwed this up.
Right. They're not all maximum, but
But
they'll
that's-
have certain values.
No.
That's kind of the graph that you have there on the left, because you're saying at that point, any one of those x of n minus 1 has about a uniform possibility.
Every child has one parent. This child had 4 parents.
Right. So in Viterbi we
Okay.
pick one, right? But there is a line there. We just pick one of them. I'm
Okay.
saying we combine all those lines to give one value to the new child or each of the new states. Not by a maximum, but by a combination of the relationship to all possible previous points.
You could do
I
that, you're
really-
just not computing the joint anymore.
But
Like you have a most likely trajectory by different criteria.
Still didn't catch the idea. I don't know if everyone else did. I know Walt did.
So like if you were to multiply the joint probability that you get out of Viterbi, multiply that by your marginal probability at that last step. So you're weighting the Viterbi to be more likely to choose something that matches the marginal. I think that's what you're saying, right?
kind of, yeah.
Yeah.
So, being a graduate class in engineering, one of the things that we're trying to do is maintain some kind of optimality in the algorithms that we're looking at. And in that case, it seems heuristic. I mean, maybe you get something, but I don't know how you could argue that would converge to anything.
Marginal.
Right, the other thing is conceptually, if you're weighting all of the possible previous parents, like on the grid, you're then, bringing in factors from these parts of the grid that are at the edges, which, really have nothing to do with that particle. And maybe, I guess, they would just be weighted less.
All of the parents do already have a weight. I mean, every one of them has a calculation of what the posterior is for that parent, and they're not all going to be equal. Some parents will be very improbable. I mean, we already have that. So if you want to kill off parents and not even bother to compute with them, it seems like probably a good way to do it is to use the posterior. I mean, the posterior is what we always want to work with. I mean, maybe you like the marginal better than the joint based on the one example I've shown you, but I think that would be hasty. I think this is a pretty darn good probability to be working with. So if you want to eliminate parents from the pool of consideration, this would be a good thing to use for. I have a feeling we're way over on time, at least for a break. It's 6:04. Let me give you a choice. Three possibilities. We can break early. We can take a break and briefly start to talk about the Kalman filter, or we can just power through to 6:30, and I'll switch over to the Kalman filter now.
What if we just end 5 minutes early?
Okay, fourth possibility. What do you guys want to do on?
Power through.
Really, you guys are okay?
No, but power through.
Oh my gosh. Gluttons for punishment, all right. All right, I'm game. Okay, so anything else on Viterbi? No? Okay.